All right, so let's get started with the collab notebook. This first video is going to be a review of NumPy, which is a framework for working with matrices and multidimensional arrays. If you feel like you already know NumPy pretty well and you don't really need this review, feel free to skip to the next video where we start talking about PyTorch. Okay, so an overview of NumPy. NumPy arrays are basically objects that you store and manipulate matrices. So here we're going to define three different NumPy arrays, each with different shapes. We have a one-dimensional one, we have a two-dimensional array, and then we have a three-dimensional array. And so let's print all of these out, and we can see how their values are represented, and we can also see that there's this property called shape that defines basically the lengths of the lists in each direction. So here we have shape 6, one-dimensional vector, and then we have a 2x3 matrix, and then we have a 3x2x3 multi-dimensional array. So you can index into NumPy arrays similar to how you would with Python lists. You can use integers or slices, but additionally you can also specify indices for multiple dimensions of the array. So in this example, we're going to create an array that has shape 4x5, and it's going to have all the values from 1 to 20. So let's print this out first, and you can see the values here. And let's start by maybe indexing into a single value of the array. So that would be row 2 of the array, so I should get the numbers 11 through 15. That's what I see here. And we can also provide indices for multiple dimensions. So let's say I want row 2, column 3 of the array. I want the number 14. So I should do 2, 3, and that's what I would get here. And finally, you can also do a combination of integer indices and slices, just like you do with Python lists. So here what I'm doing is I'm getting all the rows from 2 onwards, and for each of those rows I'm going to get the value in the third column. So that would give me these 2 rows, third values, so 14 and 19. In NumPy you can do all sorts of arithmetic on NumPy arrays as long as their dimensions match. So in this example, let's try adding these 2 arrays that are 2x3, and it's basically going to add the numbers element-wise. And sometimes you can also do these arithmetic operations on arrays whose dimensions don't exactly match, because basically when you don't have enough values in one of the arrays, the values will kind of be stretched or copied so that their dimensions do match. So it's probably easiest if we look at an example here. So let's say we have a single number 3, and then we have a 2x3 matrix. We can multiply that single number by the matrix, and what it's going to do is basically pretend that this was a matrix that was 2x3 and multiply the number 3 by each of these elements. And similarly, let's say we have an array 1, 2, 3, and then we have this Z matrix, which we defined earlier to be shape 3x2x3. And you can still add these together because it'll basically copy the number 1, 2, 3 and add it to each of these rows to get this final result here. So this is called broadcasting, when you have 2 arrays that aren't quite the same shape, but you can still add them together or do other operations to combine them. And there are a lot of benefits of doing it this way as opposed to explicitly defining 2 NumPy arrays that have the exact same shape. First, your code is more concise. Like in this example, we didn't have to create an array that just had the number 3 duplicated 6 times. And you also don't have to actually store those duplicated values. You don't have to explicitly create them or store them in memory. And there are some optimizations happening under the hood in NumPy that makes these operations run faster if you do them through broadcasting. So it's nice both for conciseness and for performance benefits. And for the most part, the way that broadcasting works is pretty intuitive. It kind of duplicates the values exactly like you'd expect. But sometimes you might end up working on something a little more complicated, and if there's ever any doubt about how broadcasting works, I'd highly encourage you to check out this link over here, and that gives a pretty nice short summary of how exactly the shapes are working out. So next there's an important concept in NumPy called axes. Axes in NumPy arrays are basically like the directions along which you can do certain things. So for example, if we have this 2D array here, we have two axes, axis 0, which goes down along the rows, and then we have axis 1, which goes left and right along the columns here. So we can do an example here where we're going to be combining values along different axes. So let's define the exact same array that we have in this diagram over here. And first we'll start by doing np.sum. So by default, if you use any of these operations like np.sum, it's going to basically combine all the elements of your array into a single number. But maybe you only want to add all the numbers along a certain direction. So let's say I want to add these three things together to get 14, these three to get 15, and so on, and these two together to get 9. I can specify that I only want to do the summation along axis 0. So here, what that's going to do is it'll only do the summation along each column, but it's going to keep those values and not combine them together. And similarly, I can specify axis 1, and that's going to do it along the, it's going to add up all the items in each row. So this way, this way, and this way. And this pretty much works with like any kind of reduction operation you could do in NumPy. For example, like max and min, you can specify axes. And so if I do the max along axis 0, then that's going to give me the largest number along each of these columns. If I do max along axis 1, then I'm going to get the largest item along each of these rows. So it's really useful to kind of understand what exactly these axes are referring to, because a lot of times you're going to be working with operations where you don't want to reduce the entire array, but you want to keep maybe one of the dimensions. So more generally, once we start talking about things with more than 2 dimensions in NumPy, it's best to think of an axis as basically the index of one of the values in the array's .shape property. So let's look at an example here where we're going to create an array with random numbers between 1 to 10. And this is going to be the shape. It's going to have 4 different dimensions, 3 by 2 by 4 by 5. And if you do some kind of reduction operation and specify a certain axis, what that basically does is combine the values along that axis, or you can think of it as that axis basically disappearing from the array's shape. So if I do np.sum along axis 2, then this number, the second index of the shape, is going to disappear, and the result is going to be 3 by 2 by 5. And similarly, you can also specify multiple axes. Like in this case, maybe I want to add everything along axis 0, but also along axis 2. And it'll do this reduction across both axes, and both are going to disappear, and you're going to be left with a 2 by 5 array. So next let's talk about, let's go a little more into detail about these shapes in NumPy and how you can reshape things to be in the format that you want. So a quick warning is that you want to be really careful about the shape of your NumPy arrays, especially when you're working with vectors where like one of the dimensions of your array is 1. So this can be kind of counterintuitive at first, but these two are actually different things. So I'm initializing one vector x that has shape 10, and then another vector y that has shape 10, 1. And if you print these out, they have the same values, or they have the same number of values at least, but one of them is going to be a row vector and one of them is a column vector. And this distinction actually matters a lot when you start doing operations on these vectors. So for example, if you multiply this first one x by the second one y, it's not going to be doing element-wise multiplication as you might expect. It's actually going to give you a shape n by n matrix, because what it's going to do is use broadcasting and basically like stretch this number 9 10 times, this number 5 10 times, and so on. And so it'd be doing like 4 times 9, 8 times 9, 7 times 9, and so on for that first row, and then second row all the way until you get n rows. So you have to be careful about this. This might not be what you expect, but sometimes this could actually be intentional. For example, if you have two vectors x and y and you want to take their outer product, this is exactly how you do it. you'd make sure that one of them has shape n by 1 and the other one has shape n, and then you can just multiply them together. But if your intention is to do something like multiply these two vectors element-wise, so I want to do like 4 times 9, 8 times 5, and so on, you're going to have to reshape one of them first so that they start as the same shape. So let's try reshaping x. So I want to turn this from a row vector into a column vector. So instead of being shape 10, I want it to have shape 10 by 1. So I can call reshape to change the shape. And what I'm doing here is basically the same thing as saying x.reshape 10, 1. Except sometimes it's kind of tedious to have to like type out the exact number, because really what you care about is you want that last dimension to be 1. That first dimension is like whatever is left. So if you put -1, you're basically telling NumPy to infer that dimension based on how many values are actually left in the shape of the array. So once we have it reshaped this way, we can see what happens when we actually multiply that reshaped version by y. So now both of these are column vectors, and when I multiply, I actually get an element-wise multiplication of these two vectors. The last thing is it's pretty common to have to add and remove axes, especially with axes with shape 1 from a NumPy array. So there's some useful syntax you can use to do this. So let's say like we have this vector y again, and it's shape 10 by 1. If I want to get rid of that last thing and turn it into a row vector, I could do y.reshape 10, and I would get rid of that last dimension. But I could also use this other function called squeeze. What squeeze does is it basically removes all the axes that have only length 1. So if I call y.squeeze, I would also get this vector of shape 10. And we also go the other way around. If we start with a row vector x, which is shape 10, and I want to add in that, that extra axis like we did before to make it into a column vector, what we did earlier was x.reshape -1, 1, and that works exactly like you'd expect. Another way to say that you want to like basically insert a new axis without having to like write out the reshaping syntax is you can kind of use the same syntax you would for indexing into arrays, but you can specify that you're going to be inserting a new axis. So what this is saying is I'm keeping all of the items along axis 0, so I'm doing x colon, but then I have a comma here, so this is the next axis, and this next axis doesn't exist yet because it's only shape 10. But if I say np.newAxis, that's going to be inserting a new axis of length 1 in whatever position I put it in. So this will give me also a vector of shape 10, 1. Sometimes you might see this syntax, like something comma none. The reason is because np.newAxis is actually just like an alias for none. When NumPy sees the value none when you index into an array, it knows that you're trying to add a new axis. Usually it's good practice to use np.newAxis instead of none, just because it's like more readable. But if you ever see none, that's what it's doing. Yeah, so the benefits of using squeeze and np.newAxis might not be super clear here, but once you start working with more dimensions, it can be really, really useful. So let's say I have just this like arbitrary vector with a bunch of dimensions. And let's say I want to remove like this axis and this axis from the array. I want to get rid of it so the resulting shape is 10, 4, 1, 6, 2. I could do a.reshape and explicitly say what I want the shape to be. Or I could just call a.squeeze and specify which axes I want to get rid of. So in this case, I'm getting rid of axis 1 and axis 3. And these would give me the same result. Similarly, if I start from like a lower dimensional array and I want to insert new dimensions with length 1, let's say I want to insert like 1 dimension here, and I want to insert 1 dimension here. I could call b.reshape and specify the shape again and actually write everything out. Or I could use np.newAxis. And what this is doing is, okay, so for the first axis, I'm keeping everything. I'm keeping this axis of length 10. Then I'm inserting a new axis of length 1 right after that. So that's where I get the 1. Then I'm keeping the next one, so I still want to keep this axis of length 4. I insert another one after that, so I have an axis of length 1. And then after that, I'm pretty much done. And I want to keep everything from 2 onwards, so 2, 7, 8, 9. And instead of having to write those out explicitly or like write out a bunch of colons, like colon, comma, colon, comma, colon, comma, colon, I can just say dot, dot, dot. And what that means is basically like give me the rest of the dimensions. And if you do that, then NumPy will like figure it out for you and keep all of those things. So finally, we can start talking about array multiplication, and this is pretty much the core of a lot of the deep learning applications we're going to be working on, just because a lot of times you can write a neural network as basically a series of matrix operations. So that's really where NumPy is really useful to us in this class. So NumPy has 2 multiplication operators that you should be aware of. There's the asterisk and there's the @ symbol. The asterisk does element-wise multiplication, while @ does matrix multiplication. So it's probably easiest if we go through an example so you can see like where they're different. Here we'll initialize 3 things. We have a matrix, 5 by 5 matrix, we have a length 5 row vector, and then we have a length 5 column vector. So kind of what we hinted at before when we were talking about shapes, you can take the outer product if you have a column vector and a row vector and you use the asterisk symbol, because that's going to be doing element-wise multiplication with broadcasting. So that would give you this outer product here. If you want to do an inner product instead, you can instead do a matrix product. So you have a row vector and you have a column vector and use @ instead of star. And that's going to be actually taking the dot product. There are usually many ways to do the same thing in NumPy. So for example, instead of doing row vec @ column vec, you can also use the dot function, and that will take the dot product just like we did earlier. If you don't want the result to be a shape 1 array and you just want a scalar value instead, there are a few ways you can do that. You can do dot squeeze to get rid of that axis with length 1, and then you just get a scalar. Or you can do the @ operation on 2 row vectors instead. So if I have a row vector and I get rid of that last dimension, the column vector, I could still do @ and it's not going to be doing element-wise multiplication because it's not an asterisk. It's going to be still taking the dot product and giving me a single scalar value. There are also some other useful NumPy operations that might be useful at some point in the class. So I'll put them down here and you can feel free to check out the Colab afterwards.